Super, I think we can begin. Excellent. Hello, everyone, and welcome to the CE Hub's Lunchtime webinar series. We are thrilled to be hosting today's session together with Oakdene Hollins. And today's webinar focuses on material strategy and building the evidence base for the UK automotive sector. And so, to begin with, there are a few housekeeping points. To start with, we are recording this event and the recording has already started. And the recording will be made available via the CE Hub's website. And so if you do not wish to be included, please keep your cameras off. Please also keep your microphones on mute during the presentations. And feel free to add any questions that you wish to ask our speakers in the chat box during their presentations. And also following the presentations, there will be time for Q&A and discussion after all of our presenters have spoken. And this is the time when you have a choice to put your camera on if you wish to put your hand up virtually to ask a question, as well as put in the chat box. Super. So just moving on to the next slide here. I have gone through housekeeping, which is great. Discussion areas, as I mentioned, the importance of value retention processes in the context of circular economy. We will also show examples of value retention processes and look at implementing value retention processes and the associated benefits. Great, so this is the agenda for this session. We have Rachel Waugh, Principal Consultant from Oakdene Hollins joining us, Alan Banks from UK Lightweighting Innovations. Alan is UK Lightweighting Innovations Officer from the Ford Motor Company, and Stefan Einarsson, who is a Sustainable Business and Circular Economy Specialist of CE 360. So my name is Zaneta Muranko. I am a fellow at the CE Hub. I specialize in design engineering and behavioral science in circular systems, and I will be chairing this event. And so moving on to our first speaker, really warm welcome to Rachel Waugh. Rachel is a principal consultant at Oakdene Hollins, as I mentioned. She holds a PhD from the University of Cambridge in engineering, which focuses on ways to halve carbon emissions in the global steel and aluminium industries. Rachel joined Oakdene Hollins in 2013 and has contributed to studies to evaluate and quantify remanufacturing markets across the globe and participates in the Auto Council's Net Zero Manufacturing and Supply Chain Group, and also had previously led on the Cars and Materials Banks projects for APC. So Rachel's presentation will outline some of the key findings for the automotive sector in the UK study of value retention. Rachel, over to you, please, for your 10 minutes presentation. Thank you.
Thank you very much, Zaneta. Well, I'm really pleased to be able to speak to everybody this afternoon on the topic of value retention processes. I wanted to start off by just giving a quick overview of what is meant by the value retention framework. This was a framework that was formalised by Nabil Nazir and a team of colleagues for the UNEP International Resources Panel back in 2018. And the framework really covers some of the central loops of the circular economy. And it has lots of really important implications, we think, in terms of resource efficiency. So it's a really well-aligned topic with the work that goes on in the NICER programme. So firstly, one of the key things about this framework is the connection to the extension of product loops. So primarily, it's about interventions that allow the life of products to be extended. And one of the key distinctions the framework makes is between interventions that happen at the end of life of a product, so the product has reached its full service life, and also those products where it might have reached its end of use, but but not reach the end of its full service life. So I'm going to quickly run through the different processes, and hopefully that will help illustrate the different roles that these processes can play. So firstly, at the higher end of the hierarchy, we have remanufacturing, and this is a really standardized industrial process taking place in factory settings, where there's full disassembly of products, full interrogation, replacement and remediation of any worn or damaged parts. And the products that come out of it typically have a full service life ahead of them. They can perhaps be remanufactured multiple times. And so you're extending the product life by that full service life increment. And typically these products will be have guarantees and warranties that demonstrate that their performance is effectively equivalent to that of a new product. As we move down the spectrum of activities, we have what Nabil and team referred to as comprehensive refurbishment. So this again takes place at a factory setting, but it might not be possible to guarantee that full performance in the same way that you have to for a manufactured product. Then we move into the processes that tend to take place once products have reached the end of use. So it might be that they haven't reached their full design life, and there might be interventions that we can apply here to extend the life significantly, but perhaps not to the same degree as remanufacturing and comprehensive refurbishment. And some of these activities may take place outside of that industrialized or factory setting. So we have refurbishment as described here. We also have repair. So this is generally where you might be fixing a specific fault. So it might not be that you're interrogating the rest of the product to ensure that it is still functioning, but addressing a specific failure. And you also have direct reuse. So a product may no longer be required by its current owner, but that is not to say that there's not useful life left within that product. So as hopefully you can see, this framework really distinguishes between the different levels of intervention required in terms of extending the life of the product, and also that distinction around whether the activity takes place in that more industrialized setting or outside of the factory setting. Now, value retention processes, like many of the other activities within the circular economy, have a lot of really tangible benefits. So in terms of some of the impacts that we see through value retention, there is this marked reduction in material demand. And this at the moment is something that we're really seeing, particularly in terms of critical raw materials. So being able to reduce reliance on imports, if you've got these critical materials embodied within your products, anything you can do to retain those materials and retain the value without putting it through any processing that might have yield losses or inefficiencies is really beneficial. A lot of the processes around value retention activities tend to have lower energy requirements and are more easily electrified. So we're not talking about melting down materials. It's akin to sort of product level recycling, and that can have tangible reduction in terms of greenhouse gas emissions, and also potentially through reducing transportation. There are lots of other benefits as well that we can see. So effectively, in a lot of these processes, what you're doing is you're displacing the processing of materials with labour. So you have the workforce triaging products that are coming in, looking at what the faults are, what the remediation activities will be, and then potentially some reverse engineering where it might be older products, and applying that thinking to actually bring those products back to a useful state. So these are generally quite highly skilled jobs. They are by their nature more localized, so there are potentially opportunities to reshore, particularly if the UK, for example, doesn't have domestic manufacturing activities for those products or materials. Also, one of the other key benefits is the ability for these products to segment the market. So typically, remanufactured products are around 60 to 80% of the price of a new product. And that means that people might be able to access new market segments if they, for example, could not access the highest price original OEM parts. And that's a really interesting feature of value retention processes when we're looking at extending the life of products, particularly looking at this automotive example. So it might be that, for example, if you have a 12-year-old vehicle, you might not want to pay for a new replacement part, but you might be happy to pay for a remanufactured component, provided it had the warranty to go with it. Other drivers that we are seeing around the value retention landscape are around increased product complexity. So one of the motivators for value retention is when you're able to remediate the product without having to spend too much time on the labour. It's the labour content that is often the factor that determines whether it's economic to undertake value retention activities. But as products become more complex, whether that's through increased integration, higher electronics content, then the price of these products is going up, and therefore the space in which value retention activities has to operate economically also increases. On the other side, we're also seeing greater push for that value retention activity in response to constraints around supply chains. So we've seen issues around semiconductor shortages, freight shortages, and lead times increasing. And there are applications where value retention can help support resilience in some of those supply chains. So just wanted to draw out some of the key results from the UK study that we did in partnership with the KTN and the University of Brighton for Innovate UK. And we saw that in terms of the different sectors we studied, automotive was one of the really strong players for value retention activities. As you would perhaps expect, the reuse market for vehicles is very well established and mature. And there is a significant amount of activity that takes place around servicing and repair of vehicles. But what is also interesting is that up in that remanufacturing space, there is significant activity. Just to say here, it's quite a challenge to get some of the data for quantifying the size of some of these markets, because remanufactured products are required to perform to the same level as a newly manufactured product. When you classify that using industrial statistics, the activity is actually classified under manufacturing. So it's quite difficult to unpick the scale of remanufacturing compared to manufacturing. But based on our survey approach and talking to practitioners, this is our current estimate of the market. So if we're looking at automotive as well as heavy duty, so that's sort of commercial vehicles, some of those off-road vehicles as well, we're seeing values of well over £1 billion in 2020. As explained, the high labour content of these activities is also an important factor in terms of the size of the activity that's going on. So we see that while small in comparison to the very large servicing market, there is a significant fraction of activity that's going on in remanufacturing in terms of employment as well. Wanted to quickly touch on some of the key barriers and opportunities that have been identified through the study. One of the challenges that we do tend to find is the fact that the practitioners might have to reverse engineer products if they don't have that full visibility of what the product contains, and particularly with the increasing use of software, that can perhaps be a challenge in terms of being able to process a product from that remanufacturing side and guarantee that performance. Also, we see that there's an increasing squeeze between the price of the new parts, but also the imports of cheap copy parts. So historically, those parts would be competing, particularly on the aftermarket, but they would be also lower quality. But we are seeing that the quality of those parts is increasing, so it is squeezing potentially that market for remanufacturing. In terms of the opportunities, the transition to electrification is a really interesting one in terms of new products that be those value, high integrated, containing those raw materials. Those products might be really attractive to look at as to their suitability for some of these processes. Also, when you're looking at the Scope 3 emission reporting, then that's really where you get to see the benefits of value retention processes, particularly if there are products that are not manufactured domestically. When you're looking at that Scope 3 and you see the emissions from producing those elsewhere, the opportunity to do that, to retain those products locally, has a real benefit in terms of reducing emissions. just my final slide. I can see Zanetta's come back on. Whilst value retention, when we're thinking about those remanufacturing, refurbishment, repair and reuse activities, is a really important way to retain the value of products. It's not a silver bullet, and we do realise that for some products and at different stages of their life, they will necessarily need to enter what we've called the material value retention process. And this is looking at high value recycling. So looking at being able to retain the value within those materials as well. And at this point, I think it's a good opportunity to hand over to Alan, who will pick up on some of that recycling story. Thank you very much.
That's super. Thank you, Rachel, for this interesting overview of value retention processes and your work in the field. So we will now hear from Alan Banks from the Ford Motor Company, who leads the lightweight structures who is the lightweight structure supervisor working in the innovation and research team. So Alan leads projects centered on lightweighting technologies that have a mass production capability, and this includes material choices from advanced steel to full composite structures, as well as using hybrid technology to produce the best value for automotive applications. Over to you, Alan, for your presentation.
Very good. Thank you very much, Zaneta. Hopefully you can all hear me. So I'm going to quickly run you through the presentation that we have here. This was a study that originally started at the beginning of last year. It was led by the UK Auto Council, where they had 7 strategy groups. They asked me to lead the lightweighting strategy group. And it was from that study that we realised that, and this was all based around the UK's requirement to get down to zero emission vehicles by 2035. And it quickly became clear that you couldn't really do a lightweighting strategy unless we addressed the advanced material strategy. And the government just don't have an advanced material strategy in the UK. So we felt it was important that, from an automotive perspective anyway, us as OEMs and tier 1s and material suppliers and academics that were in our group stayed together to actually write that strategy itself. And this is the summary of that. This is all that I'm going to present to you very horrifically quickly, so apologies if you don't get a lot of the detail of the slides. Obviously the detail is available. I'll happily share it with you afterwards if you want to get hold of me independently. But just to give you a flavour of this, so when it came to the lightweighting strategy for the UK auto sector, if we were able to onshore the material requirements that we need for the UK industry, and that's vehicles that are made onshore in the UK, they can be obviously kept onshore if they're sold onshore, but also for export. So this is only for the UK auto sector. And if we were able to onshore the advanced material that we need for those vehicles, then we would be able to reduce CO2 by 137 tonnes per tonne of material when you compare that to material from a Chinese origin, which equates to over 13 million tonnes of CO2 a year for the whole of the sector. Now, we all know that we've had struggles trying to convince our government colleagues that CO2 and greenhouse gas emissions in general are an issue. Depending on what side of the political fence you're on, you can choose to believe that or not. So where we wanted to factor this argument was that if you onshore it, then not only do you reduce your CO2, but you create jobs and you improve wealth. And we wanted to sell this as a business case, because at the end of the day, what is the government for if it's not to improve wealth and create jobs? What is their point other than that? So we want to sell this in its business merits, but understand this is entirely done to reduce the effects of CO2. So I'm quickly going to run through this study. We did this for 4 main material groups. And as I said, I do have the detail of this, but these are just the summary slides of this particular one. So aluminium, for instance. If we were able to onshore the UK requirement for aluminium for the automotive sector, then that gives us a tremendous opportunity. So we need about 500,000 tonnes of aluminium in the UK for the UK auto sector. About 400,000 tonnes of that is raw aluminium, and about 100,000 tonnes of that is casting for ingot for things like battery boxes and at the moment, obviously, internal combustion engines and things like that. So if one plant, for instance, could produce 200,000 tonnes of aluminium a year, and 100,000 tonnes of that could be sort of recycle it. So that would come from, sort of disused vehicles or even cans or anything that's made of aluminium. If we could put that back into an aluminium melting pot, for instance, then that plant would save 3.2 tons of CO2 per year compared to a European average of making virgin material. But there's 16.5 tons reduction compared to Chinese origin aluminium, which is the dominant market. As well as that, that plant would create, as you can see, 588 million pounds of GVA, and that's just from that plant directly. But studies have shown that for every pound you spend in industry, you actually get about 2.74 pounds in the surrounding areas and the supply chains to support that industry. So on a much wider scale, you actually get 1.5 billion pounds in GVA from there. Also, that plant would employ 400 people. And again, the same study suggests that for every person that's directly employed in an industry, you employ 2.54 people indirectly. So when you put that out to the greater, and obviously all of these numbers are based around a plant that will produce 200,000 tonnes, and as I said, the UK requirement is 500,000 tonnes. So the summary of that is that if you onshored the UK automotive, and these are numbers are just automotive, we're not looking at the canning industry or the foil industry or construction or anything like that, then you save 8.25 million tonnes of CO2 using 50% consumer scrap. We firmly believe that it's possible to do this with 100% consumer scrap. So it's a huge amount of CO2 that we'd be able to save. We can create and sustain just over 3,700 jobs, it says there, and we could create wealth of 2.1 billion. Now, we did the study, and again, I'm not going to go through that in any detail in the interest of time, but to actually power all of those plants with a renewable energy, so assume that we can't tap into the existing infrastructure, we have to build brand new plants. If we built a brand new wind farm, for instance, or a set of wind farms to directly power these factories, then that energy would cost us 5.235 billion pounds, which is a lot of money. But because you get a sort of 2.1 billion in the circular economy, you get payback in just 2.5 years, which is not a bad payback. Then if we look at the steel, sorry, I'm going to skip through that slide in the interest of time. If we look to the steel industry and go for a similar slide, then for every 1,000 tonnes of steel that's made in the UK, 960 tonnes of that is recycled, so you don't have to use a lot of virgin material, which is a 560 tonnes of CO2 saving compared to a Chinese origin. And again, for every 1,000 tonnes, you create 200,000 pounds worth of GVA, 500,000 pounds in the devolved supply chain and communities. And again, for every 1,000 tonnes, you employ 4.2 people and 6.6 outside. Now, the UK industry needs 650,000 tonnes, so times all those numbers by 650, and you get a significant amount of wealth and jobs being created. And the summary, again, of all of that is that we would save about 2.4 million tonnes a year by onshoring the UK steel industry for automotive. You create and sustain 7,000 jobs. You create wealth of 344 million, which is, but these are all circular economy. And again, if we were going to put all of that industry into the UK, there are existing steel plants. So obviously, if we wanted to tap into existing energies, but we again assumed that we would have to build our own plants for this, then the energy power that we'd need is about 1 billion, which is just under £1 billion. So we get payback in 2.73 years based on the fact that we get 344 million through the circular economy for that. Carbon fibre. Carbon fibre isn't a huge industry for automotive, but it will be. Now, the reason I say that is because as we move towards a zero emission future, the SMMT believe that there's going to be, by 2035, there's going to be around 141,000 vehicles running on hydrogen power. Not necessarily just automotive, but it could be in trucks, it will certainly be in rail. But just for automotive, there's 141,000 tonnes of, 141,000 vehicles running around that are going to be powered by hydrogen. Now, they are all going to need hydrogen fuel cell vehicles, which means that we have to have onboard storage, and the most efficient way of doing that is via a Type 4 tank, which is wound in carbon fibre. So we're going to need a huge amount of carbon fibre, about 11,000 tonnes actually, to support that requirement. Now, carbon fibre, albeit, as I said, it's quite a small take up in volume compared to steel and aluminium, but the CO2 production of the CO2 output of during production of carbon fibre is simply horrific. It's you know, sort of 6 or 7 times the amount that you get from steel, and it's about 2.5 times the output that you get from aluminium. So in aluminium, from virgin material, if you make it via coal, if you use coal as your power source and you get it from China, is about 20 tons per ton. Carbon fibre in the European average is about 49 tons per ton, and it's significantly more than that if you get it from a high fossil fuel sort of power base. It's like it's about 200. It's about 200% higher than that. So you can tell there's a lot there. But we know of a company, which I can't tell you about because I'm under NDA, that are looking to put a new breed of carbon fibre into the UK. They're an American company, but they want to put their factory into the UK, and that is going to have a substantially less embedded CO2 in the making of the carbon fibre itself. So again, we think that we can create wealth of about £209 million with 512 million in the devolved supply chain, create 150 jobs with 413 in the devolved areas. But we can save a huge amount of CO2. Now, obviously, bearing in mind that, as I said, we use significantly less carbon fibre compared to steel or aluminium, we save about the same amount of embedded CO2. If we're able to realise that American plant into the UK and use the new technology, then we save about 2.42 million tonnes of CO2 for a carbon fibre manufacturer, which is almost the same number as aluminium. And aluminium, as I said, is a huge number that we have there. So when we look at the summary of that, as I said, we saved 2.42 million tonnes of CO2 just in the UK production. We sustain 563 jobs. We create wealth by 721 million through a circular economy. But the infrastructure costs are significantly less for the carbon fibre line based on the new technology compared to steel or aluminium. So it's just over 700 million pounds. Obviously, it's still a lot of money, but compared to it's almost the same as the wealth that you create in this plant for running it for 1 year. So your payback is much sooner. It's literally just over a year. So there's a significant advantage of getting an onshored carbon fibre industry. Now, this was all factored for onboard storage of hydrogen, but once we have a plant that is making that carbon fibre, there's no reason, for instance, why you couldn't use it for structures or for any kind of sort of body panels and things like that. So once the carbon fibre is there and people are used to using it, then we're hoping that that will really have a knock-on effect to how carbon fibre is seen within the area. And then the last couple of slides, glass fibre. Glass fibre is tending to be used a little bit more as we move to in an electrified future, because the vehicles are getting heavier due to the battery, so we need to get that weight out. Now, glass fibre, again, we think we can take out about 104,000 tonnes of CO2 in the manufacture of glass just by onshoring, and by the use of renewable energy. The glass fibre would, one glass fibre plant to meet all of the needs of the UK industry was about 52 million with 127 million in the devolved environments, and that plant would employ 606 jobs directly, with 1,660 jobs in the supply chain. Now, what that means for glass is not a significant amount compared to the other materials, but again, you know, we see that these materials are going to be used more as vehicles become heavier. We're going to have to offset that weight due to increased range and performance that customers demand. So we save about 41,000 tonnes of CO2, but we sustain 2,200 jobs, a little bit more than that, as you can see. And our wealth increase is just under £200 million a year. Now, to either convert a new site or to upgrade a site, depending on which way you want to do it, they're slightly different in how you get that payback. If you want a new site, then you get payback in just under 4 years, and if you have a site upgrade, then you can get payback in just under 3. So again, we think there are significant sort of bonuses there. I'm going to skip past that slide in the interest of time. Those are my details there. As I said, this is a huge presentation. It took us about 18 months to get the details of this. We did it with the Aluminium Federation, UK Steel, Composites UK. So we're confident in the numbers. So if anyone wants to sort of contact me to go over that, or if you think you can help, or if you can help us advise on policy and how we realise this, we're more than happy to do it. Those are my details. Please contact me. I'll very happily take your call. And with that, I'll shut up and pass it on to the next presenter. Thanks very much, Zaneta.
Super great. There were many interesting insights on the material use strategies and associated impacts. Also, sincere apologies for now twice, I think, misspeaking the title of your role. So Alan is a UK Lightweighting Innovations Officer at the Ford Motor Company, and certainly an interesting and impactful function to play in enabling a narrowed flow of resources in the sector. So thank you, Alan, very much for your presentation. So we now will hear from Stefan Einarsson, who is a senior consultant and University of Exeter associate working in the field of circular economy and ESG management. Stefan has been involved in a number of projects related to circular economy and circular business analysis, including value chain analysis, material flow analysis, and value creation opportunities. And he has recently been working together with us in the CE Hub on projects focusing on data and the role of data pooling to enable circular value creation for strategic materials. So thank you very much, Stefan. Over to you for your presentation.
Thank you, Zaneta. Do you hear me okay?
Yes, we do. Thank you.
Hello, everybody. Nice to be with you here today. So my name is Stefan. And as you see on the title, I would like to talk to you about a value retention in the context of a particular case that we've been exploring recently at the CE Hub that relates to rare earth elements and permanent magnets, which are components that are found in many things, but increasingly in electric vehicles and wind turbines that are critical components. So this is a case example that we've been exploring within a larger project that we've been working on together with the Office for National Statistics and some other governmental stakeholders and industry. So in the context of the circular economy and value retention, permanent magnets are interesting for various reasons. So these are high-tech components and they have a long potential lifespan. There could be a permanent magnet could maintain its magnetism for maybe 200 years if it's in the optical environment. And they're found in various applications we use every day, but they're increasingly very important in strategic projects like electric vehicles and wind turbines that are critical for electrification of the society, a build-up of renewable energy, and overall the net zero transformation of the UK economy. So in electric vehicles, the magnets are used in various places, but they're in highest quantities in the motors within the drivetrains. And in wind turbines, they're in the generators, in particular the newer high-capacity generators in the turbines. And these magnets, they contain high proportion of so-called rare earth elements. And you will see examples here like neodymium and dysprosium are two examples. And the value chain for these elements is almost 90% controlled by China. So it's becoming a geopolitical issue. They're in very high demand, and therefore they're subject to price increases and volatility. And there's actually a real risk that demand may exceed supply within a few years. So they're strategically very important. So interesting to explore in that context. So the questions we set out to understand was sort of, given the current electrification and net zero aspirations, what could be the future demand for these components and materials that are needed to supply the UK with these signature projects, EVs and wind turbines? And what happens to these materials when the products reach their end of life? And we know actually currently there's almost no recovery of these elements. They are basically all lost from the economy. So what is the circular value retention potential possibly. So what are the volumes? Where are these materials in the economy, and what is the potential value capture retention potential? So in order to in other words, we want to understand the stocks and flows of these materials. And to do that, we started with a simple value chain framework that you see here. This model describes the physical flows of stuff, basically through the linear value chain. So starting from mining, through refining, throughout different component manufacturing and assembly, and to the usage stage, and then to disposal. Or as an alternative to disposal, a circular value chain, which then includes the various circularity pathways, from maintenance, as Rachel talked about earlier, contributing to lifetime extension. You can have direct reuse, refurbishment, remanufacturing, or then material recycling at the last end, where you could even do urban mining as a way of capturing value from what has already been put into disposal. So these circular pathways are where the value retention potential sits. And typically we would see the highest value retention potential at the highest level of project aggregation. So at the, in this case, the EV or the wind turbine as a whole, or the larger components of those products being the drivetrain or the motors and so on. And typically we would expect the lowest from the material recycling, although that can also be significant. So what we did is we translated this conceptual model into what we call a business dynamics model. It's basically a computerized model based on systems dynamics. It's a tool for scenario analysis. So it basically allows us to model the stocks and flows of materials, and then explore different scenarios for how increased circularity might help reduce the demand for virgin rare earth elements. And this enables us then to quantify the flows over time and basically explore the potential value creation potential and performance over time. The model has different components, so we can simulate the product demand, the volume of inflow to the economy over time based on the forecasted stock for the signature products like EVs and the wind turbines, and the outflows, what will leave the stock. That's based on the average lifespan expected for these products, and then we can translate that into demand for rare earth elements for these products. And that's based on bills of materials, so basically what the products are made of. And then we can simulate the different levels of circularity and see what's the impact on stocks and flows. And on top of this, we can add various layers of analysis, like the embodied costs, carbon, and various aspects related to that. And importantly, we try and get a picture of the value capture potential accumulated over time for the UK economy. So what you see here is the sort of rough order of magnitude outcome of our analysis, an estimation of the cumulative flows of rare earth elements over time until 2050 in for these two products, and the associated value of the materials. So only the material value, so assuming today's retail prices. So what we see is we're looking at significant volumes, both in terms of demand for electric vehicles. It's in the order of magnitude of close to 50,000 tons over the period. The outflow over the same period is over 20,000 tons. And for these groups together, we are looking at an outflow of maybe 35,000 tons, somewhere in that order of magnitude. And the material value of those outflows, which in a business as usual would be lost, could be between 5 and 7 billion UK pounds. So it's really significant. But that gives us sort of a first indication of the size of the price, basically, of seeking value retention in this area. What you see here is then how these outflows could be building and increasing over time. So on the left axis, there's the tonnage per year. On the right axis, you see the accumulated of 35,000 tons until 2050. And we see how this very rapidly ramps up. So now the electric vehicle stock is increasing fast. There are very ambitious aspirations for building renewable energy, offshore wind power and onshore. And once these products reach their end of life, we will see the outflow pick up quite fast. So here in the years past 2030, things will start picking up. And it's important that, and you see here the 100 here, that's the 100 tons per year, is the capacity of a recycling facility that is for rare earth elements being developed in the UK. Just to put things into perspective, so you can see that there would be a market or space for many of those, many times that capacity. And it's important to keep in mind that if one just starts building the post-use recovery capacity, once these volumes are already high, it will presumably be too late, because it will take years to build the infrastructure to both recover and then revalorize these assets. So it's important to start preparing that now. What you see here is then an example of how different circularity initiatives in a potential high circular economy scenario could reduce the outflow. So this is for neodymium only, so the numbers are a little bit different from what you saw before, and this is for value in millions of pounds. So the baseline is, we're talking about maybe 4 billion lost in outflow, but with a combination of circularity initiatives combining a lifetime expansion for the assets and high end-of-life recovery that we assume here that would be ramping up to 75% until 2050, we can reduce these losses to about 1 billion. So it's significant potential positive impact there. Now, to make the point that to unlock this potential, it's important to establish some collaboration between government and industry, because this transition will not most likely happen by itself. And one thing is that is important is to facilitate higher visibility of the value chain. I think Rachel mentioned this as well before, and this picture is just to show sort of the level of complexity that one needs to understand related to the physical flows in the rare earth element permanent magnet value chain. We will see that we have sort of a semantic taxonomy of characteristics that are very many of them are critical to understand, to be able to unlock and figure out what is realistic in terms of reuse, remanufacturing, recycling, and so on. So actors in the post-use value chain, those who are going to do remanufacturing, refurbishment, recycling, they basically need to understand what's in the products at this level of detail. So there are different motor subtypes, there are different magnet orientations in the magnet, they have different coatings, there's different production methods. These magnets are put into the products in different ways. It can be very difficult to get them out again. They may be glued. They have different content of oxygen and so on, many things. So it's important to facilitate visibility in the value chain and exchange of information between the value chain players, basically. And this most likely will need facilitation also by governmental actors to make this happen. And this is something we've also been exploring in our current project on how to create sort of data pooling networks to help facilitate this flow of information between actors. And lastly, just to make the point that now gave you an insight into our work on the rare earth element permanent magnets, but in principle, our methodology, our to data pooling, to do the systems dynamics modeling can be applied to whatever product, component, and material out there. So we've done this previously also for other groups like construction materials, plastics, and others, and we expect to be using refining our approach going forwards and in the context of other value chain flows. So on that note, I want to thank you for your time and attention, and that was it for me.
Excellent. Thank you, Stefan, for your presentation. Please, can we all have all of the three speakers join the room now for some audience Q&A? And so we have a number of questions in the chat box now, but also if any of the audience would like to ask a question in person to the speakers, please feel free to raise your hand virtually. And we invite you to ask the question. I'm aware of time, and I think we've got about now 12 minutes to answer your questions. So perhaps we can have a minute or two to answer each question to cover as many as possible. So just to kick off, I have a question for Rachel, and this relates to electrification of vehicles. So the question is, what does the electrification of vehicles mean for the future of value retention processes?
Thanks, Zaneta. Yeah, it's a really interesting one. I think, as I mentioned in the presentation, the increased complexity and the value of individual components may present an opportunity for greater value retention. I know that there's a lot of work that's going on in the battery space, and this ties in with one of the questions, actually, I think repurposing, which is something that is often associated with EV batteries, absolutely is an important element of the circular economy. And whilst the value retention framework I presented is one way to cut the pie, as it were, there are lots of other really valuable activities. Also, we do have a stock of vehicles, of ICE vehicles, that are going to be in use beyond the ban for petrol and diesel, and then subsequently hybrids. And we don't want to just get rid of all of those because of the embodied energy and emissions that have gone into producing them. And there's the potential for value retention activities to help service and maintain those fleets as well. So lots of opportunities going forwards, I would say.
Thank you, Rachel. We have a question from the audience. Apologies, I don't know how to pronounce your name. Would you mind introducing yourself?
Yes, it's Owen Bailey. I have one question and one comment, really. First question is to Alan. It's about steel, and just in terms of the research done, have you differentiated between the retention from EAF steel as opposed to blast furnace steel, and what are the considerations for the value streams to be circulated within the EAF route has been differentiated with the research?
Yeah, it has. So the work that we did was with British Steel, and we had Tata Steel in our group as well. So we're confident with the numbers. So obviously, to get to a more energy efficient and reduced CO2 environment, we need to be into EAF rather than blast furnace. We do understand that getting to 100% EAF is going to be very difficult, if not impossible, because you kind of need to start with blast furnace steel before you can migrate to EAF. So we, to keep the value within that. One of the things that we've tried to do in all of this is to, when we, and Rachel had it in her presentation, trying to keep the inherent value of the materials, so that if we create ultra high strength steel, for instance, and that's recycled from a vehicle, it stays ultra high strength steel once we recycle it, and it can be reprocessed as ultra high strength steel. So you don't go into a kind of general steel pot at the end of it, if you like. So yes, we have got, I'll happily share it with you, Owen, if you want to contact me afterwards to show you the full sort of waterfall chart that was produced, that has all of the blast furnace, all of the EAF, all the way down to sort of a kind of net zero environment at the end. I'll happily share it with you.
Yeah, I'll definitely follow up that. But just a general comment then, because I put something in the chat. I think we're we have a serious issue because we have industry sectors doing different things and not even considering circularity. Well, actually, not even considering decarbonization, but let alone circularity. And we have government policy being developed on I suppose, the wrong sort of information, in my opinion. And I said I was at the Marine Energy Wales conference this week, and there wasn't one mention of decarbonisation in the manufacturing process. There wasn't one mention of circularity in anything that was being discussed. And I've just come from another workshop this morning around the steel sector and the UK government research. And again, they're talking about resource efficiency, but in the context of a linear economy, not in the context of a circular economy. So I think we have a lot to do to make sure that we get this message through into industry and into policy as well.
Yeah, just I think to pick up on that point, Owen, I think there is perhaps a danger that sometimes when you're talking about products like EVs, you're talking about wind energy, because they are by nature green, you can sometimes focus on, you can not look at the full life cycle of it, and actually having that upfront design for circularity and then connecting the loops at the end of life is absolutely something we need to be doing, particularly for these products that we are anticipating are going to have significant demand, and we're going to be investing a lot of our materials in them. So yeah.
Yeah, well, we're already making a big mess with our so-called renewable sector, so we need to get away from ourselves and start doing it properly, really.
Absolutely.
Great, thank you. We have a question in the chat from SEin around repurposing. So what is the role of repurposing in value retention processes? And I direct this question to Stefan.
The role of repurposing in the value retention. This might be more for Rachel and her taxonomy on remanufacturing and so on. But I think it's a term that I think relates very much to the refurbishment, remanufacturing. But you might be then repurposing something for it with different purpose than it was originally. So you would be reusing it, but for maybe in a different product. So I think if I would say an example related to the case that I was presenting earlier on the magnets, then one example could be that you would take a magnet and you would chop it down into smaller pieces and repurpose it for a different use. So maybe in a electric scooter, it might come from a vehicle, but could become a repurposed magnet and an electric scooter, for example. So I mean, it definitely has an important role in the reuse space. I think Rachel might also have more on this.
Just a few short points, just so we can get some more questions in. Yeah, I'd say it's a really hot topic. Again, if I'm thinking back to EV batteries, it's an area where, for example, there is some pilot activity going on looking at could you use end-of-life EV batteries for stationary energy storage systems, and there are people doing it at the moment, and it's an ongoing exercise, I think, to understand truly, what should be that balance between repurposing and recycling. And there are so many factors that will come into that, some of which will be market driven, so raw material prices. There could be policy implications. We've got the revisions of battery regulations going on at the moment as well. And I think it's going to be a watch this space really in terms of seeing what happens. And it's just trying to keep that really agnostic view and not inadvertently back the wrong horse.
Thank you. There is a question in the chat box from Atanu. It is about product passports, digital product passports. So how do you foresee use of digital product passports as an enabler for decision making in remanufacture or refurbishment? Perhaps a question to Alan.
Yeah, that's a very good question, actually. One that I'm not entirely sure I have an answer for. Yeah, I think it's going to be really important to do some kind of material tracking. Otherwise, we're going to lose sight of where something is. There's no doubt about it. When it comes to an end-of-life vehicle, for instance, if we want to make the vehicle as light as possible, it probably means that we're going to be putting some really high-value material in a very inaccessible place when we want to dismantle it. And the way that we dismantle vehicles is still probably going to be by shredding. We may do some sort of manual taking apart, but I would imagine that's going to be quite rare, which means that you need to understand where that material is. And once you've got it, you need to understand what you're going to make it into. And I think one of the issues that we've already faced is that we want to stop people putting aluminium into an aluminium box, if you like, just so when it gets remelted, it goes back into sort of 2000 grade aluminium when it was 6000 grade and it was really valuable. If you lose that kind of value in the value stream, then yes, you know, we've kind of shot ourselves in the foot. We've done the right thing, but then we've executed it badly. So it's the execution of it that I think we need to work on there. But yes, I agree. I don't have an answer for you, Atuna, but yes, I agree. It's something that the whole industry needs to understand how we're going to do material passports.
Rachel or Stefan, would you like to comment on product passports? It's really a hot topic, and there are more comments than that in the chat box about them. I wonder whether you...
Yeah.
Maybe...
I think I agree with Ellen. I think a form of product passport is, of course, a very important aspiration and will be an important tool in the future. But I think nonetheless, we are probably... it's quite complex, and as we could maybe see from a little taxonomy picture, there's really a lot of data layers that would have to be brought together across the whole value chain. So we're seeing some challenges across those initiatives that are out there, you know, in battery space and so on, and sort of getting this to a practical or sort of operational level. I think it's very important, and the whole issue of data and visibility is crucial to enable the flow of circular flow of material. So it's absolutely a very important thing to keep working on.
Yeah, just to build on that, I think, yeah, absolutely, it's really hot. It's coming in the batteries regulations. There are lots of projects looking at it in electronics, for example, and there's a as I think one of the things that Owen mentioned was about the risk of looking at things in product silos as well. Is there an opportunity to look more broadly across the suite of products where we're going to be looking at passporting? Also recognizing that all of this data has a cost. It's going to cost people time, effort, administration to collect this data. So we really need to know why we want this data and what's the purpose, not just for recording, but also for driving better design, better decision making, better information for customers. So lots of information.
Super. Conscious of time, this was a really short and sweet but very informative session. Thank you to all the speakers. Just on the questions asked in the chat box, if any of you in the next minute in the audience have any more questions, please put them down. We will ask the speakers to answer them, and we will incorporate those questions in the end of the webinar recording. So a great overview from Rachel on remanufacturing and other circular processes that can facilitate value retention, and also a really good presentation from Alan with many interesting insights on the material use strategies and the associated impacts, as well as finally another great contribution from Stefan on the value retention of raw earth elements for permanent magnets and associated net zero strategy. So for any of you in the audience who would like to connect with our speakers, please contact them on the details they've provided in their slides, but also I'm sure you can also connect with them on your social media platforms, potentially via LinkedIn. Thank you all. We will now come to close. All the best.